All right, so welcome to Unit 1B. This is from Unit 1 where the bulk of the questions get asked on both the multiple choice and the free response. It's also where you get a little bit more into the weeds. So just important to pause the video whenever you see something that you don't remember or want to go back to. And make sure to find sample problems to test some of the topics that you find more difficult in this part of the unit, because it'll definitely pay off on the AP exam. This is a good portion of the AP exam and also the basis for everything that follows. So we start with this discussion about parameters versus statistics, and essentially what we find is that they're really the same thing. They're a way of describing a quantitative set of data. A statistic is a value that describes a sample, and a parameter is a value that describes a population. Examples of statistics and parameters could be a minimum, a maximum, a median, a mean. You see them on your screen. But again, if you're taking the mean of a sample, that's called a statistic. Okay, and we have a symbol for it, x bar. If you're taking the mean of a whole population, then we call that the parameter value. That would be another symbol, which is the Greek letter mu. We typically use Greek letters when we talk about parameters. Okay. When we talk about center, measures of center specifically, I alluded to this in the last video, we have two main ones, the median and the mean. The median is just the midpoint of the distribution. It literally splits it in half. To find the median, of course, you have to arrange the data values from lowest to highest. It would not make sense to pick the middle value of an unordered list. You have to have an ordered list, and then the median is right in the middle. So if it's an odd number list, literally the value in the middle. If it's an even numbered list, it would be the average of the two in the middle. And we have this nice little trick that right now is being cut off, but it says the position of the median is n, your sample size, plus 1 over 2. Okay, and make sure you don't forget that plus 1. And again, if you get in like a 0.5, that means you need to take an average of the two values on either side of that value. The mean, on the other hand, is the balance point of a distribution. Okay, so it's the arithmetic average. And the way that you find it is you add up all the values in the list and you divide by the number of numbers. Again, our symbol for the sample mean is x bar. Our symbol for population mean is mu, the Greek letter mu, lowercase mu. And the example that we had when we got to this section in the class slides was catching these fish. And we essentially said we had 6 fish. One is 3 inches, one is 4 inches, one is 5 inches, one is 6 inches, 8 inches, and 10 inches. And we wanted to find the balance point of the distribution. That would be the mean. And the explanation that we gave for balance point was if you add up all the deviations of the individual values from that balance point or that mean, those deviations should add up to 0. Naturally, some of them are going to be negative, some of them are going to be positive, some might be 0, meaning that value is the mean, but when you add them up, you should get exactly 0, and that's a way of checking that you got the correct mean. And please note that from this point forward, when we talk about deviation, we do value minus mean, not mean minus value. So the actual value, so the 4 inches minus the mean of 6 inches. When we talk about the mean versus the median, one of the things that we need to remember is there's a relationship between where the mean and median lie and the relationship between that and the shape of a distribution. So in a skewed left distribution or skewed right distribution, the mean is pulled towards the tail. Okay, we say mean is a non-resistant measure of center. It is sensitive. Okay, whereas the median is resistant. So the median always stays at the 50th percentile. The mean is pulled in the direction of the skewness or the outliers. And so in this case, in a skewed left distribution, the mean is lower than the median. It's pulled towards the lower values. In a skewed right distribution, the mean is higher than the median. It's pulled towards the higher values. And when a distribution is approximately symmetric, then the mean will be roughly equal to the median. And that's an interesting trick that you can use. We'll remind you of that in a couple of slides. So again, all it says here is that if it's roughly symmetric with no outliers, the mean and median are going to be roughly the same. But where it's skewed or you have outliers, the mean tends to be pulled in the direction of the skewness or the outliers. The median is what we call resistant, okay, meaning the presence of outliers don't significantly affect where the median is. but the mean is not. And it's important, and you're responsible for, in an FRQ, choosing an appropriate measure of center, not just a measure of center. Now you can also describe the position of each individual data value in a distribution or a data list. And a percentile is one way that we can do that, where the percentile of an individual value is the percent of values in a distribution that are at or below in value as that data value that you're describing at the moment. And for most things in life that are positive, like IQ or your score on some standardized test, you want a really high percentile, right? So if you score, for example, in the 95th percentile for the SAT, that means 95% of test takers scored at or below your score. Of course, a high percentile isn't always a good thing. You could be talking about something negative like nights spent in prison. And then, of course, you'd want a very low percentile. You want the majority of the public to be far above your value for nights spent in prison. So you want the percentage that are at or below you to be very, very, very low. And again, you can see that when you actually have to calculate the percentile for an individual data value, it's very common that they'll give you a graph like a stem plot in this case. And what you are going to do is you're going to count how many of the values are at or below whatever value they give you. So just make sure that you include that value in the at or below calculation, otherwise you'll get a value that's slightly off. So a graph type that we haven't seen in quite a while is the CRFG, or the cumulative relative frequency graph. And in this graph type, we're actually plotting the individual percentiles for all of the different individual data values in the distribution. And so, of course, for the lower values in the distribution, we're going to be, at the beginning, we're at 0, and we're going to go all the way up as we go forward in the distribution, all the way to the last value. That'll have a percentile at 1 or 100%. And again, we haven't seen this one in a while, so it might be worth pausing and reviewing this one here. Next, we make it to describing variability or spread, and we alluded to this in the first video. The most common and the most elementary measure of spread is the range. And most of you probably learned this one in elementary or middle school, but it's just the maximum minus the minimum. Very, very simple. Just make sure that if your list is unordered, that you actually search and double check that you got the correct max and the correct minimum, because if you miss one of those values, then you're definitely not going to get the correct value for the range. Please note the range is not resistant. Okay, so just adding one outlier or taking one away can completely change the value for this measure of spread. Is a pretty good illustration of that fact, right? We've got 3 different distributions, and if you just look at the range, it looks like all 3 of the distributions have similar or the same variability, right? The range for all 3 of them is 5 because the max for all of them is 7. The min for all of them is 2. But looking at them visually, I can see that A has much more variability than C, for example. And this is a reminder that range is not resistant. It is not a resistant measure of variability. So maybe we want to find something a little bit better. And one idea is to look at the individual deviations of the individual values from something like the mean. And one of those measures could be the standard deviation, and this is, as you know now, a concept that permeates the entire course, keeps coming up over and over and over again, but it measures the typical distance of the values in the distribution from the mean. And what you see on the bottom here is the formula for standard deviation, which is the square root of the variance, but the actual components of it are you're taking the individual deviation of each value from the mean. So you need to find your mean first. You can't find the standard deviation without the mean. You take the individual deviations, value minus mean, you square them to handle the negatives and the positives. You don't want those to cancel out. You add them all up and divide by n minus 1 when it's the standard deviation for a sample. We've got a couple important properties that you should be familiar with, particularly for multiple choice questions. Standard deviation is always greater than or equal to 0. You can't have a negative standard deviation. Larger values of this measure indicate greater variation. So in the real world, we want as small a standard deviation as possible because, again, the world is an unpredictable place and it's easier to predict when there's less variability. It is not resistant because every single value is taken into account, and it measures variation about the mean specifically. Another measure of position that is really, really important, and again we use throughout the course, is a z-score. And a z-score tells us how many standard deviations above the mean an observation falls. This says from the mean and in what direction, but again, it's really above the mean, and if it's negative, then you know it's below the mean. The formula for z-score is here on your screen, but it's value minus mean all over 1 standard deviation. So the numerator of this equation is the deviation, and when you divide it by the number of standard deviations, you get your z-score, okay? And it's important that you remember that you can't just say distance from the mean or away from the mean, that if you're going to use that language, you also provide a direction. Is it above the mean? Is it below the mean? Because that matters. In terms of measures of spread, here's another major throwback from the beginning of the course. We've got the interquartile range, or the IQR, which is a better measure of spread for sure than the range, but even better than the standard deviation for certain types of distributions. We'll talk about that in a minute. But the whole concept behind the IQR is that we're dividing our distribution into 4 quartiles, where each quartile represents 25% of the data values. And we've got 2 key locations on the distribution that matter for the IQR, Q1 and Q3. Q1 is the median of the data values that are to the left of the median in an ordered list, or the 25th percentile. And Q3 is the corresponding median, but for the upper half of the list. It's also the 75th percentile. And the IQR is just the distance of the inner quartile from Q1 to Q3. So we do Q3 minus Q1 to get the IQR. Now, it's important that you choose a correct measure of spread, an appropriate measure of spread, just like you need to pick an appropriate measure of center. So mean and standard deviation are always paired together, as are the median and the IQR. The mean and the standard deviation are not resistant. They're what we call sensitive. The mean and the IQR are resistant. And so we use the mean and standard deviation when our data is approximately symmetric with no major outliers. We use the IQR and the median to describe data sets that are either skewed and or have outliers. So we talked a little bit about identifying outliers early on, but now we're going to talk about specific methodologies that you can follow in order to identify them that are approved on the AP exam. It's important to look for outliers because they could represent in the real world values that are inaccurate, something remarkable that it's not likely to occur again, so maybe you don't want to build it into your prediction model. And of course, as we've seen with non-resistant measures of both center and spread, they can really disproportionately influence those values. So you got to be careful with outliers, and you want to identify them when you suspect that they may be present. We've got 2 methods for doing this identification. The first is the 1.5 IQR rule. I'll just highlight a couple key things. So for both methods of outlier identification, you're going to have both a lower and an upper fence. And there's a couple key differences. So in the 1.5 IQR rule, you are finding that the lower fence is any value that is below Q1 minus 1.5 IQRs. And again, you find an IQR as just Q3 minus Q1. Upper outliers are outside of the high fence, so higher than Q3 plus 1.5 IQR. And it's a common mistake to do mean or median plus and minus the 1.5 IQR. So again, you're going from Q1 minus 1.5 IQRs, or you're doing Q3 plus 1.5 IQRs with method 1. With method 2, you are starting from the mean and adding and subtracting from the mean 2 standard deviations. And this is, method 2 is our 2 standard deviation rule. So a lower outlier is anything below 2 standard deviations below the mean, and an upper outlier is anything above 2 standard deviations above the mean. Now that we've got all of these measures defined and that we've refreshed our memory, we can talk about how to make and interpret a box plot. So box plots are made, they're very zoomed out bird's eye views. They are extremely high level because they're only made with 5 values. And those 5 values are our 5-number summary, which is the minimum, Q1, the median, Q3, and the maximum. And again, the box plot just abstracts away all the granular details so you can focus on the big picture of where the distribution lies. Now, it may look like there's a lot of steps to follow, but making a box plot is actually pretty easy, and your calculator can make it itself. But just make sure you select the option on the TI-84 or the TI Nspire that has outliers drawn separately, as you'll see in the example here. So the way that we would make a box plot by hand, if you're asked to on the AP exam, we start by calculating our 5-number summary. So min, Q1, median, Q3, and the max. We identify any outliers using the 1.5 IQR rule, specifically when we're making a box plot. And then we actually make the box. So you put a tick mark at each of the 5 values. You connect them in the way that's appropriate, with the box in the middle representing Q1, the median, and the Q3. And then you draw out the whiskers all the way to the min and the max. What's very, very important that you don't forget is you might not actually make it all the way to the min and the max. If any values are identified as outliers using the 1.5 IQR rule, you're actually going to draw the whiskers only to the lowest and the highest value that are not considered outliers. All values that are considered outliers need to be drawn with asterisks outside of the whiskers so that they can be easily identified as such by your reader. We can see, and again, it's not best practice to do this, so I would be very shocked if they asked you this question on the AP exam. It's much easier to see shape from one of the more granular views, like a stem plot, like a dot plot, like a histogram even. But if you are ever asked to identify the shape of a box plot, you can see skewed left on top. You can see that lower quartile is really, really big. That means that the values are very spread out in that 25% of the data set, as opposed to the upper quartile, which you can see is much, much, much smaller. And again, I like to compare the first with the fourth, the second with the third, and only when they agree, I'm willing to say with any certainty that I understand the shape of the distribution from a box plot. But even then, it's better to ask for a more granular view. So you can see what roughly symmetric looks like, and you can see what skewed right looks like. It's, of course, pretty much the opposite of what skewed left looks like. And I already mentioned this, but just remember to draw your outliers with the asterisk outside of the whiskers. Okay, we then get to this portion of Unit 1 where we're talking about transforming data. Now, a transformation affects all of the values in a distribution. This is not adding a value to the list or adding a constant to one or two values in a list or a distribution. These transformations of quantitative data affect all values inside the distribution. And we've got two main types that we studied. The first is adding or subtracting a constant. Okay, so you should know the rules. If you forget them, you can actually test this on your TI-84, and if you have questions about how, you can message me at this point in the video and I will send you a quick blurb on how to do this in case you forget. But these are fairly easy to remember. If you add or subtract a constant from every value in a list, then measures of center and position are going to be affected by that constant that you add or subtract. Measures of spread or variability are not, and the shape does not change either. Another type of transformation that we can do is multiplying or dividing a distribution by a constant. So again, that's every single value in the distribution being multiplied or divided. And this transformation type affects all measures of center, all measures of location, all measures of spread. The only thing that's not affected by this transformation type is the shape. Okay, so it's just, if it was skewed right before, it's still going to be skewed right, just a little bit more stretched out. And again, if you're dividing by a positive constant, it's going to be more contracted, but it's the same shape. If it was skewed right, it's still skewed right. If it was approximately symmetric, it's still approximately symmetric. Awesome. So moving on to common FRQ topics for Unit 1. The absolutely most common topic is describing distributions of quantitative data. So remember, that's SOX plus context. The other very, very, very common FRQ type is comparing two distributions. And so it's important to give context. It's important to touch on each of the letters in SOX: shape, outliers, center, and spread. And remember that outliers can include any unusual feature. It's important to do it in context and to use comparative language. So notice you have to use words like larger than, less than, the same as, different than when you're describing the shapes. It's not enough to just do SOX twice when you're comparing two distributions, but go letter by letter comparing the two distributions. You can pause the screen here if you want to read this comparison of household size in South Africa and the UK. So just an overall review of where we are so far in Unit 1. When we want to explore quantitative data, we want to plot our data, so we want to see it visually. It's a little bit easier to understand what we're looking at if you see a visual rather than a list of numbers. We want to look for the overall pattern and then any departures from that pattern, such as outliers, gaps, clusters, etc. We can use numerical summaries to describe center and spread, and what we're about to shift to, which is the last part of the unit, is what to do when we've got a very complex model that we want to simplify, and we're going to use a density curve to simplify the description of a model or distribution. So density curves lie above the horizontal axis. They all have the exact same area underneath them. That area is exactly 1 or 100%. And this is a view of how you can take an approximately uniform distribution on the left and convert it to a uniform density curve that you can use to answer certain questions. This is the example of Selena, our lazy employee who works at the airport bookstore and who has been taking the train, but now they have this walkway that's opening up. And in this case, you can see how you can simplify a histogram that looks approximately symmetric to a density curve that's just a smooth curve touching the majority of the tops of those bars. Density curves have properties that are very similar to the distributions that we've been studying all along. So the mean of a density curve is the balancing point of the distribution. The median separates equal areas, so 50% at or below, 50% above. Nothing there has changed. And of course, when a distribution is skewed, when a density curve is skewed, the mean is going to be pulled in the direction of the tail. We then shift to study a very important distribution that comes up throughout the entire course. I'm sure you agree with me by now, the normal distribution. And all normal distributions have the same structure. They're symmetric, single-peaked, and bell-shaped. We have two different parameters that we use to describe a normal distribution: the mean, which we signify by the Greek letter lowercase mu, and the spread or variability, which we use the standard deviation sigma to talk about the variability of a normal distribution. Again, because a normal distribution is just a density curve, the area underneath it is 1. Why is it important to study normal distributions? And this comes up on multiple choice questions all the time. It's because there's a lot of things in the real world that can be modeled by the normal distribution, so standardized tests, repeated measurements of the same quantity, like anything that's manufactured, like the length, the width, the height, the diameter, the height, the weight of different manufactured qualities. Characteristics of biological populations, so things like the weight of chimpanzees, adult chimpanzees, that follows a normal distribution. And of course, as we just finished inference, you know that you use the normal distribution in the majority of the inference procedures. That's why we're checking that normality assumption. We've got an empirical rule, so if you actually want to know if something is normal, you're not just going to check that it's bell-shaped, symmetric, and unimodal. You're going to actually check these mathematic properties. So we know that the empirical rule says how much data we can expect to find within 1, 2, or 3 standard deviations of the mean in a distribution. And if this checks out approximately, you can say that a distribution is approximately normal. If it checks out exactly, then it would be exactly normal. And just remember, this applies specifically to normal distributions, so you can't use the empirical rule for any distribution other than the normal distribution. distribution. Now, we want to find areas in a normal distribution all the time, and you can either find them in a raw normal distribution with some mean and standard deviation, or you can first standardize a normal distribution. So the standard normal distribution is centered at a mean of 0 with a standard deviation of 1, and we might want to find the area under a specific segment of the curve to answer different questions. These are very, very common on the AP exam. So how do you do it? How do you find the area in a portion of the normal distribution? It's customary that you draw it. Remember, you can get points on the AP exam FRQs just for drawing the curve and shading it properly. And so you want to actually draw the normal distribution again, mean and 3 standard deviations on each side of the mean. You're going to want to shade, so actually make a vertical bar at the lower bound or the upper bound and shade in whatever direction that the problem specifies. And then you're going to use either table A, the standard normal distribution table, or technology, a function like normal CDF, in order to find the area between the shaded region. Now, we've done so many normal CDF problems this year that most of you just skip to the final step of using the calculator, plugging in the values, and writing down the correct answer. And that's okay, but where people often get it wrong or mess up the calculation is when you want to work backwards, when you're actually given the area and you want to find the boundary value. And that's when we have the inverse of normal CDF to use, or inverse norm. And the example here says the heights of 3-year-old females are approximately normally distributed with a mean of 94.5 centimeters and a standard deviation of 4 centimeters. And they tell you 75% of 3-year-olds are taller than what height? Okay, so you know that there is some height above which 75% of 3-year-olds are, and below which, by the way, 25% of 3-year-olds are. And they want you to find that value. That's where normal CDF is not useful. That's where inverse norm can be super helpful. But again, it's best if you draw the curve. That way you can realize what it is that you're actually trying to find. Again, most of our calculators don't have the tail parameter, they're left-tailed. And so you're going to want to draw that distribution so that you can see that the boundary value has 25% of the values to the left of it. And either, again, you can use inverse norm or you can use table A. In either scenario, you'd get your correct answer. In this case, we find out that 75% of 3-year-olds are taller than 91.8 centimeters. That's the same as saying that 25% of 3-year-olds are at or below 91.8 centimeters. And just like that, we've concluded our first unit's complete AP stats review. Unit 1 in the books. You've got additional resources that you can use to prepare you for the mini assessment that's tomorrow. If you don't feel comfortable yet, you can check out Khan Academy, you can check out AP Classroom, you've got the Google Drive to assess yourself and see where you stand, and then you can obviously focus in on those areas that you find need most improvement. And don't skip the review of the common FRQ types. So again, for Unit 1, you can be asked to describe quantitative data sets. You could be asked to describe 1 or 2 variable. So 1 variable you can describe, 2 variables you can compare distributions, so comparative SOCs. There's also common FRQs with normal distribution calculations, inverse norm, and normal CDF. So again, just review a couple, can't hurt, and have a great night, and we'll see you tomorrow.